So in short, the goal of this is to optimize that economic performance under a number of technical performance constraints. How rapidly can I ramp up or down my reactor system, my hydrogen production system? What's my grid resilience constraint? Will we always be able to match that? Do we need to bring in secondary sources like a natural gas-fired system in order to ensure grid resilience? Those are the types of things that go into that. Now, I mentioned that this is complementary to those other efforts. So we start with the system and look out, and many of those other tools out there look at the much broader ecosystem of generators and understand when would we add an additional component that looks like this. So they meet in the middle there. So these other complementary efforts that are out there don't necessarily get into the reactor safety, the nuclear system safety, nuclear system operation, but we do that and then look outward toward those other tools. So we have a lot of capability that's very unique to the nuclear system components with regard to the quality assurance levels, safety and licensing aspects, reactor operation. This is a human system simulator laboratory that we have at INL that is a digital control room mock-up for a nuclear reactor facility. We can put a number of different plant designs behind that screen and understand how this would operate under a number of different scenarios. So we're in the process of connecting this with our systems integration laboratories. We can look at the performance of integrated energy systems. So looking at that laboratory, you saw some of these facilities, materials and fuels complex, and human systems simulation laboratory. If we focus in on systems integration, this is the laboratory where I spend time. In the center here, we have our high temperature electrolysis skid that's complementary to what NREL is working on low temperature electrolysis. We have our grid emulation systems. Outside this wall, we have some renewable components, but we can also connect this up to the National Wind Technology Center, get better data sets, better information from facilities that are made to look at that more specifically. And we're in the process of building out our thermal energy distribution system. This is our representation of a nuclear reactor in the system. So when we want to look at how do we optimally connect and operate and understand different failure scenarios, what happens if my coupled load of my hydrogen system or my electrical load fails, how's it going to impact my reactor? Well, we can do this here by using essentially a smart electrical system that behaves like that reactor would. So this is in procurement right now, where we will initially look at emulating a pressurized water reactor, but then we're also building out a microreactor test bed that allows us to look at a number of different reactor types as well. And this couples currently to our steam electrolysis system, which is also coupled to a chemical synthesis reactor, so we can look at use of that hydrogen in a number of different products. We have wireless charging, so I mentioned looking at a number of different charging types. Battery testing is in another bay, just back over that side, and the bay over that side of the laboratory is on biofuels. So we have a number of components of these integrated systems right here in this single facility that we can then look at how we couple and how we might operate the system overall. We also have a lot going on in the space of new reactors. I want to highlight one project that's with NuScale Power to build the first small modular reactor in the US. Now, this isn't a research reactor, it's not a demonstration reactor, it is a full commercial facility. This particular reactor design includes 6 separate reactor modules. Part of that project is to use one of those modules to support research and development activities. So that's some of the fun I get to have once this is available. We get to go do some research on a commercially operating reactor facility. That's a very unique opportunity. So one of the primary areas for that research is integrated energy systems. That is the highest priority. So what we learn in that non-nuclear laboratory, we can translate out to this laboratory. What we're learning with current fleet reactors, we can translate to these small modular reactors and understand how we might operate those differently and how this can port out much more broadly in the commercial sector. So we do a lot of work hand in hand with industry to ensure that what we do in the laboratory is informed by industry need and that it has a commercialization pathway. So one thing I want to highlight is GAIN. That's the Gateway for Accelerated Innovation in Nuclear. Nuclear facilities often are unique, and there are very few across the laboratory system. GAIN is a way for industry, for universities, to access those facilities. To come in and get a small voucher that helps to pay for working with those researchers, working with those scientists and engineers, designing a test program for a new nuclear fuel or your system overall. How do I come in here and make sure that I'm doing the right thing with facilities that I can't have in my backyard? So GAIN is a very good platform for that. And other laboratories can work together on these GAIN vouchers as well. It is access to those capabilities. Another exciting area, in August of this year, the National Reactor Innovation Center, or NRIC, was announced. NRIC focuses on enabling testing and demonstration of reactor concepts by the private sector, validating advanced nuclear concepts, resolving technical challenges. So again, another way to advance these technologies to ensure that we look at energy systems in 2030, 2040, that these options are available to us, that they're not just theoretical, but this center, this capability, will work with many of those developers to demonstrate those concepts so that they can be licensed and deployed in those timeframes. So a couple of words on partnering with INL. We have a number of user facilities. We lead the nuclear science user facility platform that includes facilities at INL, but it also includes facilities at universities and other laboratories in the nuclear space. So if you're looking at a new material and you want to understand, is that radiation resistant? Take a look at how you might address that through the use of some of those user facilities. We work with a number of strategic partners, cooperative research agreements, small business opportunities. University partnerships are many different ways to work through that. We have a number of visiting researchers, joint appointments, internships. I mentioned our National University Consortium. The Nuclear Energy University program is a little bit unique across the DOE-funded laboratories in that, by law, the funding that is put into research and development under the Office of Nuclear Energy is automatically 20% of that goes toward universities. So if you're interested in doing something in that space, this is why when I have a $10 million budget, I don't have a $10 million budget. 20% of that comes off the top to go to universities. So if you are interested in working in that space, this is a great opportunity to apply to that. Those can have partners in industry, they can have partners at laboratories, but that partnership, non-university, non-academic partner, is limited to 20% of the funding in that proposal. We've also started a graduate fellowship program, and we have a number of named postdoctoral research opportunities as well that are a great entrance into the laboratory. Last year, we published this 50 States Impact. It was a really good insight to this little place up in Idaho, relatively speaking, how we're impacting actually across the U.S. and Puerto Rico. So it's a great place to take a look. If you're interested in where we might be touching your laboratories, your universities, your state in general, take a look at that. It's pretty impressive. So with that, it's 10:30, time to switch, and I hope you learned something.
Peter up. Sandia. Okay. You all set? Yeah.
Morning, everybody. More PowerPoint slides for you. So, but thanks for sticking around for this last session. So, just wanted to offer up what Sandia has, and again, we're part of this this global family within the U.S. National Lab System. So, we're run a little bit differently. We're a National Nuclear Security Agency run lab as well, which means we do a lot of weapons work, and then we also do a lot of energy work. And we started the energy work about 40 or 45 years ago, about the time that MREL was stood up as well, as a hedge from the energy crises of the 70s and so forth. And so we have a lot of facilities that we can leverage as well. And so I can call up Jane Smith down the hallway that's working on some weapon system. Can we use your lab? So we don't have to pay for it out of our energy programs. We can just use the facilities and so forth. So that's our benefit, as it were. And we focus a lot on engineering sciences. So like Doug spoke about having like a nice set of sort of global models that all the labs can use, like Reed is one example. So we might be the providers of, what's the parameter space of technology A? What are the error bars? And we can give that technical information and feed it into more popular, more well-known models. Then with argon, we've done as well in hydrogen systems, so we'll point to that. So again, we all work together, we specialize, and then we cross-pollinate. So it's a nice ecosystem, I think was a great word that Shannon used. So I'm Peter Kobos, so I manage the water power and technologies program. So that's, we think about hydro dams, not that, everything else. So think about marine hydrokinetics, so buoys that bounce around in the ocean, generate electricity, current energy conversion, things like this. So effectively it's a robotics lab that I kind of lead up these days. But I wanted to show you the sort of global context at Sandia, and this is just sort of a primer on going through the slides. So there's a lot of material here, but the main focus is on the left-hand side, some of the areas that we touch on, as well at the lab, and then some of the foci, as it were. So we really look at trying to de-risk early technology. So really, again, basic energy, engineering sciences, does it work? And just like Doug spoke to and Shannon did, if it doesn't work, I don't really care how much it costs. So the engineering science have to work first. So I use the thumb sometimes, does it work? And if yes, then tell me about how much it costs, not the other way around. So science comes first. So. And we test and verify a lot of technologies. Our hydrogen program, for example, we have a location in California. And that's about 1,000 people out there for the Sandia site in Livermore, California. Globally, our company is about 14,000 people, so it's getting pretty big. And it's like 7 mini companies, as it were. So just as a context. So take that for what it's worth. So technology teaming with international standards, we do that a lot as well. So ASME and so forth. And then partnering with industry. So trying to work with technology, either sort of inventing it and getting patents and R&D 100 awards, as all the labs do, getting it out, and or vice versa. A company comes to us, can you test this? Can you shake it? Can you burn it? And then we say yes. We'll break your technology and tell you how to improve it. So, but all joking aside, it's a great ecosystem. So there are a lot of components at Sandia, and like I said, it's like 7 mini companies. And across the energy space, I'll focus on here for the obvious reasons of our audience here today. So a lot of pieces that I'm in my daily pieces are involved with. I can point here. Well, I'll just point. Close enough. The record here, may I assume. So renewable energy is a space that I work in most intimately. Energy efficiency as well, and grid. So we're all kind of in the same space. And I'd say these two are the daily operations that I work in. Nuclear energy fuel cycle and safety and security as well. We work a lot with INEO and other labs as well. This is the NNSA space, and that's less in my daily life. But the punchline to take away from, honestly, this whole presentation is that Sandia works in all the energy spaces. So nuclear, fossil, renewable, and then everything in between, grid. And so we have specialization pieces, but if they're global models, we look to NREL for it. If there's a certain subject matter expertise in nuclear, we often look to INEO for it. So again, we all partner well together. As I mentioned, well, Sandia is pretty big, and we've been around a while, since about the late 40s or so, part of the Manhattan Project, just like INEO, the nuclear complex. And so there are a lot of facilities that we can leverage. So we have a lot of facilities that they're a little bit more modern now for grid and so forth. So high power computing, I think we have 3 high powered computing platforms. And so we can run those computational fluid dynamic models for other weapons related work. And then some of my guys and gals, my department, also cross-pollinate. We can go use their supercomputers, get in the queue, a month later you can run it. But these are things that would take decades to run on a normal computer, and we can run them in a day or 2 or 10, depending on the size. And so we can look at like wakes from turbines, wind turbines as well. A particular project we're looking at is steering that wake as well. So not necessarily looking at the next generation, but how can we improve what we have now? And so we can actually turn with the controls of the wind turbine, and so offset the wake. And so what we can do there is, again, is you that way you can improve the power optimization across an existing fleet, as well as what we're finding out, and they just put, I think, a patent in for this, was about you can actually control the output of the wind farm that way. And so you can match the load a little better. It's a few percent here and there, but a few percent across tens of thousands of wind turbines is pretty serious energy. So, so we're excited about that. And we're partnering with NREL on lots of these projects as well, just up the road at the Flatirons facility and then down their Golden campus as well. So this is just say we work across the energy spaces for a while. And a lot of the really cool stuff, and I have some pictures we'll get to, but we look at big testing, burn it, shake it, those kind of things. Some of you might have been familiar with the LNG work we've done in the past. It's called the Phoenix Project, and I'll get to that, as well as the crude oil characterization project, and I just want to highlight those right now. And this is us right now. We have buoys in my department that we go to the MASS facility, the Naval Test Facility in Bethesda, Maryland. It's about the size of an American football pitch, as it were, and it's about 16 feet deep. So it's like an aircraft hangar, but there's a pool in it that makes like a wave park, as it were. And they test submarine hulls and ship hulls, and they like to have us there. And it's a great partnership where we can test our devices there also. So in a little bit more realistic part. We're in the desert in Albuquerque, so we joke that we have a lot of beach, but not much water, right? So we go to the water. And similarly, not the national lab map, but similar where Sandia is in terms of energy facilities. We're in, I think, over a dozen states right now. We have regional test centers for photovoltaics and so forth. And we're in Alaska as well. And so there's a larger Arctic science push as well of late for lots of reasons. When the ice is melting, there's a lot more things going on up there. And we've been in Alaska for decades as well. And some unique large-scale, in particular, renewable energy facilities that we have. We have the National Solar Thermal Test Facility, or NSTTF, so the Power Tower. And so that's been there for, we had our 40th anniversary last year or so. And so this was the largest power tower research one in the world for, I think still maybe in terms of research. There's a few more scattered throughout the world that are operational as well. There's one in Spain, there's one in California, and there's a few others under construction. And looking at molten salt loops, so basically a thermal battery as well. So when the sun goes down, you still have a lot of heat and you can keep your generator spinning. And so we've had a lot of research there as well. And so a lot of engineering sciences. If you ever come out to Sandia, you'll probably be shown this. It's one of our flagship things to come look at, the big field of mirrors or heliostats. And really neat. We have family day, and so you bring your kids and they have solar cookies and you know, those kind of things. So it's a good crowd pleaser. Photovoltaics Systems Evaluation Lab, or PCEL. And this is real-time testing, which is to say we will take certain photovoltaic panels from mostly US companies and put them out there and let them cook in the desert sun for decades. So, and then understand what really happens. And so what we found is that the silicon is often pretty good. A lot of times the backing is not so good. And so that still causes the module to fail. And so understanding these types of things that don't really show up in accelerated lifetime cycle testing is a unique aspect of this facility as well. And then we have the SWIFT facility, Scaled Wind Farm Technology facility, as it were, in near Lubbock, Texas as well. And so it's a partner complementary capability to NREL's facility right up the road here as well. We have a different wind resource, so it's nice that between the two labs, we can cover different areas of the resource. Ours is more windy most of the year, but within a certain speed profile. And then NREL's is very windy during other parts of the year as well. And so again, for the national presence, we have we cover all the bases, and it's great. So, and we cross-pollinate research, staff go back and forth, a lot come up to NREL. So it's a nice friendship partnership in the research space. Just to talk about, as Shannon did, we have national impact. So everything from drill bits. So Sandia, I think it's 40 years ago, invented the drill bits that I think 90% of all the wells drilled today use. That has synthetic diamonds that are stuck to the drill bit to basically chew through the strata. The challenge there was it's not that other people weren't working on it, they couldn't get it to stick. And so we figured that out and then licensed it out. And now, well, fracking and so forth is really due to, many technologies, one of which was ours. And so we point to that pretty frequently. Wind turbine blade manufacturing. So we run a blade workshop at Sandia, and this is in partnership with NRL as well. And we've held it for many years, I think over a decade or so. It's every 2 years, and so NRL folks come down and we come up and so forth. And it's really understanding the twist and the different degrees of freedom. And as wind blades get longer and longer, there's an efficiency that goes down, but the net effect is the efficiency of the whole system goes up. But we're talking about the blade lengths are getting so long that we have trouble transporting them across the United States on roads anymore. So there are test facilities on the shores now, just so that we can ship in these types of blades. And so there's, how do we do that? So we work with Oak Ridge as well, and just saw the mold that we've used at NRL's facility yesterday. So again, we all work together and have different specializations. So I mentioned concentrated solar in the lower left there. Improving wave energy devices, so in my particular group, we've already increased the power up to about 300%, and this is real, this isn't simulated. It's basically having control software be more optimized, as it were, but also computationally not so expensive that we need a little, like an iPhone on every device that's floating out there. They have to be computationally cheap, but also very effective. And so when I go to cocktail parties, what does this really mean? It's like, well, your traction control on your car, it keeps you from skidding. You kind of want it to nudge you to keep you in the right place. Well, this control system, it kind of pushes back on the wave. And so it spills off some energy, but it also gains more. So the net effect is it boosts power dramatically. And this is shape agnostic. It doesn't matter what your buoy or device looks like. There's no really common type, like the 3-bladed wind turbine that we all know and love and see on the horizons. That took many iterations through the decades to happen. Right now, there's about a dozen different archetypes or designs in wave energy devices, and there's no really one set. So this can port to any type of shape. So we're kind of excited about that. I mentioned P-Cell, and then I hinted at R&D 100 awards in the energy space in particular. We have quite a few, as do the other labs. NREL has a whole wall of these as well. It's very impressive down at the Golden facility. So just touching on renewables here a bit, floating offshore wind energy turbines is something that may be coming to the U.S. It is in terms of research, and where are we going with this? We don't have offshore wind farms in U.S. waters, and they're very prevalent in European waters, and what can we learn from that? And so we're looking at vertical axis wind turbines as one idea. The center of gravity is lower, so it's not going to tip over as much, and take a little bit smaller profile, and the platform costs are dramatically lower, and that's a huge portion of the initial cost. So we're trying to get better performance. Again, the thumbs, does it work? And oh, by the way, we know the cost is already lowered, and so this is something exciting that we're looking at, again, in partnership with NREL in particular. And so we have lots of folks working on this. Renewables and water power, so this is my daily life. So we have the mass basin I mentioned before. We have the power takeoff and design and testing facility. I'll just see if I can play the video because it's probably more exciting to you than watching you talk about slides. Let's see if this pulls up here. Yeah, thank you. Thank you. All right. I'm so glad last to get all the tips. It's getting harder. Let's see. All right. Okay. Go away.
Wave energy converters, or WECs, are devices that generate electricity from ocean waves. The SWEPT lab is the Sandia Wave Energy Power Takeoff Lab, and it's designed to test the generator and power takeoff systems of wave energy converters. The power takeoff and generator systems are a very essential component of wave energy converters. They essentially act as the link between the mechanical energy in the waves and the electrical energy that you're trying to produce.
This system is designed and built to simulate a device in the water. Once you're out there in the water, there is little access to the generator system. So we want to make sure that once they're deployed, the system works well.
The SWEPT lab is located in a series of shipping containers, and that allows us to be mobile and perform tests here in Albuquerque as well as other locations. The one key component of our work here at Sandhya is that we're able to leverage our troops from defense and robotics on this project and apply their expertise to this unique problem. Swept Lab is designed to simulate the input that we see in the ocean waves, but do it in a very controlled environment. So the hydraulic systems that we use here mimic how the ocean waves affect the wave energy converter and give that input to the power takeoff or generator system in a very reproducible, systematic way that allows us to study how the generator is operating and if it's performing as designed.
Wind power is oscillatory by nature. And so what we're trying to do is to design control systems and generator systems that work well in these conditions.
The oscillatory motion from the waves must be translated into a steady current from the generator. And so the Swept Lab takes a number of components and creates that oscillatory motion. It allows us to get a very accurate representation of the WEX system that we're trying to simulate. We can do things down to as small scale devices, or we can go all the way up to full scale devices as well.
Bigger devices produce
So that's the
more power,
generator of
but at the same time
that's
they're
right
more
here.
expensive and they're more difficult to build, more difficult to deploy. More devices produce less power, but they're much easier to build and deploy. So that is a question that, for which we still don't have an answer.
The attractive thing about collecting energy from ocean waves is that filtering effect from the sun to the wind to the wave kind of creates a smoothing. So the wave energy, at least in most locations, tends to be very consistent throughout the day, month to month, and that's very attractive for people who are trying to keep the lights on. Another big advantage of wave energy is that wave energy resources tend to be co-located with population centers. Something like 50% of the world's population lives within 50 miles of the coast, and that's where waves are located.
There's a lot of power available in the ocean, so from that point of view, it makes sense to try to design and build these devices. It's the challenge of solving problems that haven't been solved yet, and it's real. So we're working with real machines, we're building them, and we're helping companies to deploy these devices in the water.
We're not talking about maybe improving the performance of these devices by 1 or 2%. We're talking about maybe doubling the performance of this device. So the ability to have such a large impact and potentially make these devices commercially viable and help create an industry, that's pretty exciting.
So that's where teaming with other labs really pays off benefits. So where we can focus on the power takeoff unit specifically for certain archetypes of devices, we can offer this knowledge, and we've patented. We have 2 patents. There's I think 4 more in the works that are already submitted. And the reason there is that what we really want to happen is to have other industries take this technology and run with it. By patenting it, it prevents one company from taking it, patenting it, and then preventing everybody else from doing it. We're trying to help the industry, and this is very much an edict from the DOE Water Power Office and ERE. So it's a really nice sort of progressive model that we're trying to work with. So let's see, I have a sync here. Keep going. Okay. So in water power, just to wrap up, we also do materials testing. So we have a large materials testing lab, really a whole division at Sandia. Some for weapons, a lot for not, but there's several hundred people there as well. So we can try and leverage the size where it's appropriate for our smaller programs. So in water power, we have about a $10 million annual budget, give or take, with some carryover. So that's the size versus the entire lab is $4 billion with a B. So we're feisty. We have to be. So. And then we also work 50-50 total partnership with NREL on system design software, so it's called WEX Sim. So it's kind of like CAD software, using the term loosely, of course, but we can design devices in the software space, and I say test, understand the performance characteristics, and then one can build it. So you try and optimize it before you have to build it. These things can be very expensive because they're all new and prototypes, but we try and keep the materials costs down. So basically marine grade steel is what we want to build these things out of. It's cheap, there's an industry, there's a pipeline, people know how to build these things. We're working on the guts, so basically control systems and the generators that are a little bit new, because we've taken generators off washing machines. If you think about what does this a lot, just like a wave, well, washing machines will pull it out, and some of the industry folks have used that. but it's a different cycle. It's not just this, it's this, and it kind of stutters and so forth. So these things break, they're not designed for it. And so we're designing a whole new generation of generators that are oscillatory in nature. It's not it's rotational, but not just unidirectional, it's bidirectional and stuttered, as I say. So there's a lot of engineering challenges to make these things work long term. Energy Economics Conference, let's show some costs. And the takeaway here is that there's some graphics of all different archetypes, and Sandia led this a few years ago with collaboration with NREL and Oak Ridge and PNNL as well about, we call it the reference model. How much might these archetypes cost? First cut. So it's sort of the first design. And so they're pretty expensive, even on paper, as it were. So we're looking at, for wave energy converters, upper left there, the high end is, $1.50 per kilowatt hour. And that's on paper. Realistic, it's not far off, right? They're pretty expensive. The current energy converters, the CECs, we work less on in terms of prototypes, but the economics can be more favorable. But in reality, we're working in the water, and things get very expensive very quickly. Something we point to globally as a community, Sandia was involved as well as other labs, but there's a large, it looks like those old lawnmowers that one would push, have those little blades that kind of click. I'm seeing a few nodding heads. Something like that, but imagine it's the size of a semi-tractor trailer itself, so very, very large. Take that, sink it on the bottom of a river, unidirectional spins, and it can now power a very remote village in Alaska that's 1,200 homes. Right, so, please.
Just a quick comment, because if I think about island nations which are running off of imported diesel gensets, 31 cents a kilowatt hour is not that expensive.
Right.
Most of that power is in the 35 to 45.
Yeah, good point.
Thinking about renewable, non-fuel dependent, zero.
Other value propositions. Yeah.
It's actually a different value proposition, so it's not that far off for a lot of producers.
Thank you. I'll give you $1 later. That's exactly where I was going. There are other reasons to have these types of technologies. We can think of, after a hurricane comes through, it hasn't been built yet, but one could imagine, you bring in diesel generators, but maybe you can't get generators there. You could float a whole array of these things out, and you have an extension cord from the ocean, right? Power. And it'd be expensive, but it's a lot better than having nothing. So, and then you get fresh water out of that. You get desalination technologies hooked up to these things. You get a water well out of the ocean, and there are companies working on this. Really fascinating technology. So, but thank you, Doug, for pointing that out. Grid storage, just to say that we work in this area quite a bit as well. We have 3 energy storage groups, 2 in weapons, 1 in not, and so we can leverage the other 2 for the expertise. Some in batteries. We've looked at compressed air energy storage and many other pieces. Again, increasing reliability as well. So we work with private companies to say, will this work in their area? And area saying their regional constraints physically, the rate structure, as well as, quite frankly, what do they want to pay for? And is it long-term or short-term? Or is it the acute, the lights are off for a few days? Or are we trying to look at, okay, we want a backup power for a month, those kind of things. Grid modernization area, we've worked quite a while in this area as well. Just to say that we're working with a lot of other labs, and so including NREL, one of our great managers up here now. He took a job here at NREL. So again, there's great collaboration across this space. And again, we leverage the capabilities between the labs because nobody's exactly the same. And so again, we can leverage this and keep things cheaper for the taxpayer, quite frankly. 5 minutes. I get a timeout call. Yeah, fair enough. So fossil energy, so Chris and I know each other for many years. We worked with NETL for many years, a lot on carbon capture and storage. This is sort of the middle set of work here, the Southwest Partnership, on a regional partnership on carbon sequestration. We have a lot of geosciences. Again, sort of an offshoot of some of the weapons work, but we understand cores, we understand downhole drilling and things like this. Sandia is the national lab responsible for the technical side of the Strategic Petroleum Reserve, make sure the salt caverns are resilient enough to maintain the capability of the drawdown rate by law. It's like a 90-day supply for the U.S. At any given time. And so do the caverns break? Well, occasionally, and then we go build a new one or make sure to maintain them appropriately, so O&M, things like this, but a lot of geoscientists there. This is the fun stuff I wanted to show. I alluded to it before. So the Phoenix area of LNG pool fires. After 9/11, a lot of folks want to know about security issues, and so one can imagine with a lot of LNG talking about before it was importing back then, and then the fracking technology revolution flipped it on its head. Now we're talking about exporting, but the fact of the matter is, if we have LNG tankers moving around the world, they can be pretty serious danger, security risk. So if something happens to them, it could be a very large explosion. So the Coast Guard commissioned us to look at, okay, what happens if one of these, if it's an accident or if it's intentional and it blows up? How far off is the standoff distance? And the takeaway is you want to be about 2 miles away from these things. If you're about a mile there, if you're roasting your marshmallow, it's going to go up in flames. If you're 2 miles back, you'll nicely toast your marshmallow for s'mores, right? So you want to stand back, but in all seriousness, it gets that infrastructure built out. How far do terminals have to be for fueling or taking that product off? And with that, so we had that. Let me go back one. So we built this lake, and this is about, I think it's 180 meters across. There's a pickup truck for context. It was like a Ford F-250. And so this little dot right there, so that's the size, and this is basically one of those cryogenic type orbs that one would see on an LNG tanker. Turn it on, all right, get somebody out there, so all right, you drew this short straw, you have to throw the match at it, boom. And we can see how big the pool fire is, and there's actual LNG spilling across the water as well, and pretty serious. But we have a whole area that we can do this type of research, so it's an engineer's dream, right? And so based on that was a few years ago. What we have here now, there were a lot of fires there, and they're fatal fires with the Bakken crude coming from Canada down on rail cars into the U.S. as well. And there's a pretty serious fire that unfortunately killed a lot of folks in Canada a few years ago. And so Transport Canada, the U.S. DOE, and some other interested entities want to know, is there something different about this particular oil? Is it more volatile? Does it have more VOCs come off of it? When you basically pump it out of the ground, it's warm, now you put it on a train and you shake it for a couple 100 miles. Is there an extra danger? Is there an extra security risk there? And after, well, we started blowing up train cars worth of oil, more or less. We did pool fires to start, and then we did also other types of fires. So there's different types of crude that we looked at. And so again, throw a match at it, see what happens. A little more complicated than that. But the nice takeaway is no. There is nothing different about that particular set of petroleum, but we didn't know that. And what that really meant was that could change, again, standoff distances for trains, what the regulatory components of who can bring what on what train line where. And so it might have actually changed how oil was transported around the U.S. It could even, one can imagine if not trains, then our pipelines going to be built, things like this. So it had a very serious implication for decades of build out of infrastructure. And so we just finished that up as well. And I'll respect the time here. Nuclear energy, so we work in pieces of it in concert with Neil as well. Something we've been working on for several years now is the Brayton cycle. And so this is using, instead of water for the steam cycle, we're using supercritical CO2. And so why bother? Well, it's the Cournot cycle we all know and love, or think about going up the efficiency curve is way up the efficiency curve, much more efficient, thermally speaking. But CO2 corrodes things at different rates, and that means new materials, which means more cost. And so we're looking at that, and we ran a monetized techno-economic analysis. This is Tom Drennan, some of you may know his work, and so he's still working with Sandia as well. But again, our very small laptop-sized model is more of a techno-economic analysis. And so where are we looking at the LCOE for this particular sized device? And we have different cost curves as well. So the red dot corresponds to the cost of there. So understanding where's the trade-off? Again, efficiency, materials, economics. So thumbs, does it work first? Tell me economics second. We work a lot in hydrogen, have a whole group out in California and Sandia, working on a lot of standards for the economics crowd here. So Anna Lord and I, who's a geologist who works in the Strategic Petroleum Reserve, and some others developed a small techno-economic analysis many years ago. And I know Jackie, we spoke about this earlier. So we're trying to understand, again, how does it work, and then we'll put some numbers to it. And so we can store, not even in theory, in reality, hydrogen in salt domes, because salt self-seals, and it's actually a good media. So there are a few facilities around the world, but they're lined. So it's basically a large steel bubble underground. But you can think about these are large tanks, as it were, underground, which keeps the economics, reduces the economics. So if we think about fleets of vehicles, like the LA Basin, where would we build these large storage areas? And so that paper speaks to this. And it was, okay, thank you, Chris. We worked on hydrogen ships. So right now, somebody invented it, got some patents. When a ship comes in to shore, like a cruise ship, they either run their engines and they're docked there for a while, which means that local area in Alaska is starting to ban these. The San Francisco Bay Area is concerned about this as well. There's a lot of emissions off ships that people might not think about when they come to dock. Now you've busted your EPA limits, right? And you want to try and address that. Can you plug that in? Sometimes they do, but that means it's a lot of electricity off the grid, so it still doesn't help. What about fuel cells? These are modular, we can move them. One guy invented this, did it in Hawaii, demonstrated it. Now he started his own company in the Bay Area, and he's building a fuel cell powered ferry in Alameda right now. So pretty neat stuff. And then Seattle is also looking at hybrid ferries as well, decreasing emissions, keeping the performance up. Fantastic. So work in biofuels, but for the sake of time, we'll keep moving. Look at transportation. So Doug mentioned the Co-Optima Consortium, which is the largest consortium across many national labs and industry and university, and so Sandia is involved in that as well. We have a combustion research facility in California, which is say we have cylinders that are literally, you can look inside them, both visually, but more specifically diagnostically, and understand not just computational fluid dynamics, but you can match your CFD models with actual observable data and then calibrate them better. So we work with many large companies, including Caterpillar. We work in analysis. That's not really necessarily our forte as much in terms of the energy open space, but we have specific areas. So for Puerto Rico, for example, we're developing some models, as Argonne has well, and we've gotten awards for it. And we develop creative frontiers where we put certain assets to keep the grid up. When we won an R&D 100 award there. So these are, again, looking at the niche space, the microgrid, as well as the resilient node cluster analysis tool. So if we wanted to put microgrids across the U.S., where's maybe the best place? It doesn't have to be optimal, but is it near hospitals, is it near universities? So you have to load, so you can amortize those costs across the entire year instead of being an isolated one that can be very, very expensive. So looking for the entry point in the market. And with that, thank you all very much.
So we're at our time. Yeah, I probably should answer one better, but it's just such cool stuff. So it's hard to, kind of say no to keep hearing it. But yeah, I guess I'd encourage anyone just to come and talk to any one of our presenters, and if you have any further questions with them, and we'll just give them all around applause again. Thanks. Yeah, good stuff too. Everyone does good stuff. It's a lot of great work. Yeah, do some questions and.
Yeah, what would you thought you showed these very nice